Hello and welcome to lecture 4 of module 3. We were considering solving linear algebraic equations using Gauss elimination, and then we looked at Gauss-Jordan and LU decomposition method. And in the previous lecture where we left off with was a question that if the equations are slightly modified to the following form, what we are going to obtain when we solve those equations, and that form was x plus y or rather x1 plus x2. We had x1 plus x2 plus x3 equal to 4, 2x1 plus 2x2 plus 3x3 equal to 8, and 3x1 plus let me just check the equation that I had given, 3x1 plus 4x2 minus 2x3 equal to 9, and this also number should be 9. Okay. So originally the equations that we had were 2x1 plus x2 plus 3x3 equal to 7. Instead of that, now I have converted the equation to 2x1 plus 2x2 plus 3x3 equal to 9. This keeps our solution the same. If you recall, the solution was x1 equal to 1, x2 equal to 2 and x3 equal to 1. So 2 plus 4 plus 3, that is 6 plus 3 9, and the same equation satisfies same solution satisfies these three equations as well. So let us write down A and B matrices in the typical way, and the matrix A concatenated with the matrix B is going to be 1 1 1 2 2 3 and 3 4 2, and the last column will be 4 9 9. As we have always been doing in Gauss elimination, we will now do the first step, which is to use row 1 to make this element and this element 0. So the step 1 is going to be R1 R2 minus 2R1 and R3 minus 3R1. Okay. Remember, to put it in a consistent form, so far we have been writing as R2 plus negative 2R1, and that is because we needed the alpha values in that form. Right now we are not worried about that, so I am just writing it as R2 minus 2R1. Okay. So when we do an R2 minus 2R1, the first row of course remains the same, that is 1 1 1 4. The second row in now becomes 2 minus 2 equal to 0, 2 minus 2 equal to 0, 3 minus 2 equal to 1, and then the final number 9 minus 8 equal to 1 again. And when we do R3 minus 3R1, we will essentially get 0 1 2 minus this would be minus 2. So minus 2 minus 3 will be minus 5, and 9 minus 12 will be minus 3, same as before. Okay. So at the end of step 1, this is what we actually get, and what we see over here is that this element, the A22 element after the first row operation, has become 0. As a result of this, we will not be able to continue the row operations any further, and the reason for that is that in step 2 the operation that we will need is we will need to compute alpha 32, which is A32 1 divided by A221 and negative of this, that is the negative of the ratio of the coefficients. And now the A22 value that we have gotten after our step 1 is 0. As a result, this cannot continue, Okay, this cannot continue because A22 has become 0. Okay. In an example of this sort, what I have done is taken up a specific example so that A22 actually becomes equal to 0, but oftentimes what we find is that A22 need not necessarily be equal to 0, but if it is a very small number, for example if we had instead of 2 over here, if we had say 2.0001 and then 1 over here, in that case when we subtract those two numbers, the difference between the two numbers becomes a very small number, and what we had seen in the previous module is that we do not want to subtract two numbers that are of a very large magnitude but very close to each other. So that means we want to avoid subtracting 2.000001 minus 2, that kind of operations we need to avoid. So this is not just true in the case where the diagonal term becomes 0, but numerical problems in Gauss elimination method happen even under conditions where the diagonal term is non-zero, but the difference between the two terms ends up being much smaller than the value of the two terms itself, and we had seen this how this affects the overall results and the error during the error analysis part of this course in module 2. Okay. So what we have done so far was what is typically called as a naive Gauss elimination. Okay. For reasons like this, as well as for the reasons of minimizing the round of error in Gauss elimination, this method of naive Gauss elimination that we have been talking about is not used in the form that we have discussed so far. Instead what we use is Gauss elimination with pivoting. Okay. Now I had referred to what pivot means in one of the earlier lectures in this module. Okay. Pivot is going to be basically the element aii in the ith step. Okay. Why it is a pivot? Because at each ith step for doing any of the row operations in ith step, one of the most important characters playing a role in that is the diagonal element in the ith row, which is the aii. This is the element that is going to divide the overall the entire for the entire row operations. This is the dividend in case of finding this coefficients alpha 32, alpha 42, alpha 52 and so on and so forth. So in step 2 the pivot element is A22, in step 1 the pivot element is A11, so on and so forth. So if we were to write our matrix, a general n dimensional matrix in the form A11, A12 and so on up to A1n, A21, A22 and so on up to A2n and An1, An2 and so on up to Ann. So these elements are going to be the pivots during the first step, second step, third step and so on and so forth. Okay. The idea of pivoting, or more appropriately the idea of partial pivoting, comes from the fact that if you have n equations, okay, so in this particular case when we had 3 equations, our labeling these 3 equations as equation number 1, 2 and 3 was our choice. We could have very well called this particular equation as equation number 2 and this equation as equation number 3. What it means is that if we were to interchange these rows, so if this was to become row 2 and this was to become row 3, the solution does not change. So the row operations under which the solution does not change of course are the scalar multiplication of any of the row, or taking linear combination of any of the 2 rows and replacing the one of the rows with that particular row. So that particular operation does not change the result, as well as interchanging the 2 rows does not change the result. So in this case what do we do? The first thing we will do at this particular point is realize that this element is a non-zero element, and because this element is a non-zero element, we will interchange row 2 and row 3. Okay. When we interchange row 2 and row 3, okay, what we will get is 1 1 1 4 0 1 minus 5 minus 3 0 0 1 1. Okay. And now if we look at this particular A matrix is in the upper triangular form. Because this matrix is in the upper triangular form, we can go ahead and start using back substitution at this step. Okay. So what is done at each step is to look at so for the ith step we will look at the entire ith column, okay, and the A value that becomes that has the largest absolute value in the ith column, that becomes that should become the pivot element. That basically means is in this if say AI1 is the largest element amongst all of these rows, the first thing that we will do in step number 1 is interchange row 1 with row I. Okay. That is what we have done over here in row 2 and row 3. So the idea in partial pivoting is so we will interchange the rows so that AII is the term which has the largest absolute value in the entire ith column. Okay. So in that case, for example, in step 1 what we will do is we will take a look at the entire ith column A11, A21 up to AN1. Let us say A51 is the largest value amongst all of these. In that particular case we will just interchange row 1 and row 5 so that the value of the diagonal element becomes the largest. Then we will proceed with step 1. Once we finish step 1, we will then, once the step 1 is over, we will then reach a matrix of the form A110, A22 1 1 blah blah blah. Okay. And this also I am representing now with superscript 1 because of the row operation, what might have happened, we might have ended up interchanging the rows. Okay. So this is the result after step 1. Okay. In step 2 our A22 becomes the pivot element in the sense that now we want the largest value in this particular column to appear at A22. We do not look at the rows above the second row, we will only look at the rows below the second row. Keep in mind what we do in Gauss elimination, we are only interested in eliminating the elements or the coefficients in the pivot column. We are only interested in eliminating the coefficients in the pivot column below the diagonal element. So we are only eliminating A32, A42 and so on up to AN2. So again in this particular case we will compare the absolute values in this column, and then we will do any of the row interchanges that might be essential in order to get the highest absolute value in this particular column. Okay. So now let us go back and see how our overall procedure will be modified for an example of this type. Okay. So let's write down that example once again. It was 1 1 1 4 2 2 3 9 and 3 4 minus 2 9. Okay. So, this is our A comma B matrix, and our step 1 is partial pivoting. Okay. And in partial pivoting we will look at the first column. In the first column the largest value is this number 3 over here. As a result we will interchange rows 1 and 3, and partial pivoting, the operation we will do is this row interchange, which basically will lead us to 3 4 minus 2 9 2 2 3 9 1 1 1 4. Okay. After getting this particular matrix, what we need to do is, with the interchange row 1 we will now eliminate this element and this element, which basically means then the second set of operations we will do is R2 plus minus 2 divided by 3, because this is the element, this divided by this is the alpha value. So, R2 plus minus 2 divided by 3 multiplied by R1, and R3 plus minus 1 by 3 multiplied by R1. Okay. So, we will do that particular operation, and this will end up in 3 4 minus 2 9, and this we will definitely get this as 0, and this will be 2 minus 8 by 3. Okay, so 2 minus 8 by 3 should be minus 2 by 3, and then we will have 3 plus 4 by 3, that is 9 plus 4 13 by 3. Okay, and this will have 9 minus 6, that should be equal to 3. Okay, and over here we will get a 0 over here, and 1 minus so 1 minus 4 by 3, that is minus 1 by 3. Okay, then we will get basically 1 minus 1 by 3, that is really going to be 0 over here, and then 1 minus 1 plus 2 by 3, that is going to be 3 plus 2 5 by 3, and here we will get 4 minus 3, that is going to be equal to 1. Okay. So, this is perhaps what we are going to get, unless I have made a calculation error over here. This is what we will end up getting after step 1. Now, in step 2 what we will do is again look at the pivot. Okay. And now our column 2 is what we will be interested in, and the largest absolute value is minus 2 by 3. We are not interested in looking at the sign of the number, we are only interested in the absolute value, and the largest absolute value is minus 2 by 3. As a result we are not going to do any row interchange. So, pivoting will result in no row interchange or no row exchange, and then we will do R3 plus minus negative of minus 1 by 3 divided by 2 by 3, that is 1 by 2, negative 1 by 2 multiplied by R2. Okay. And when we do this particular operation, this element is going to be equal to 0, and and we will get a non-zero entity in this particular element, and we will then be able to solve this equation in order to get the solution through the back substitution method. Okay. So, I will not continue the procedure any further over here, I will just stop at this particular step, but the whole point over here was to introduce you to the idea of partial pivoting in Gauss elimination. So, in general any of the Gauss elimination softwares that you will find available for on online or any of the partial Gauss elimination softwares that you would write, you will always need to include the partial pivoting over there. For relatively smaller problems, you need not do pivoting at each step. You can you may only do the pivoting if the diagonal element at any step becomes equal to 0. So for example, you may actually follow the procedure that we used over here. That means we did not do the pivoting over here initially. Okay, what we actually ended up doing is we ended up doing the first row operation for first step with row operation on R2 and R3, and when we found R2 was equal to 0, at that time we interchanged this row 2 and row 3. We can, for smaller size matrices, we can actually try smaller size matrices which are well conditioned, we can go ahead and do the naive Gauss elimination until we reach a 0 in the diagonal element, in which case we will have to do the row interchange. But in problem of any practical interest, it is always better to do pivoting at the partial pivoting at each step,